Hello everyone, welcome back to the session relevant to adsorption. In the last session, we were just looking at adsorption versus absorption. One aspect is that adsorption refers to accumulation of the relevant compounds on a particular surface of the media, right? The media can be granular activated carbon. But absorption, which typically is sounding similar to adsorption, is where you have dissolution of the particles into another phase. So, two different phases completely, and the relevant compound of interest penetrates the phase entirely. So, that is what we see. One is adsorption, accumulation on the surface, the other one is dissolution. Let us see. Here we are going to talk about, whenever we say adsorption, we are only going to talk about this accumulation of the relevant compound on the relevant surface of a particular media, right. So, what is it that I am talking about and in what context? So, until now in my water treatment, I removed suspended solids, right, suspended solids, various mechanisms, and then I removed pathogens, right, by disinfection, and depending upon the relevant calcium or magnesium, I would have removed them here, let us say, and then gone on to looking at pathogens. But in some waters, you will have some organic compounds which are not removed during these different stages that we have looked at with respect to water treatment. So, I need to remove these organic compounds, but key aspect here is that we are talking about the end of the treatment train or unit process, let us say. So, it will be just before pathogens, or if it was for wastewater, it will be at the end of the relevant treatment process. So, this granular activated carbon based or adsorption based technique can be, or typically be deployed at the end of the treatment train. And in general, we are trying to remove organic compounds in the relevant water, those which are relatively more hydrophobic, as in they do not want to be in the water. So, what are you going to do? You are going to provide a friend, right, which they want to be attracted towards, and that is your media, right. And how does it look like? So, here we see this particular what do we say, figure, and here where is the relevant inlet here? Okay, influent is coming in, and you have the carbon bed surface, let us see, carbon activated carbon bed surface, yes, and then the effluent goes out here, right. So, while the water passes through this activated carbon, which is relatively porous, the activated carbon is going to adsorb the organic compound. So, the water does not have this organic compound anywhere, but it is changing phase. I will not say phase in its entirety, because it is accumulation on surface, but anyway it is not in the water, it is being removed from the water. The organic compounds of interest are being removed from the water. So, this is what it looks like. We will come back to this again later, right. So, adsorbent and adsorbate. So, two aspects. Adsorbent is the adsorbing phase, as in here what is the adsorbent? It is this carbon, activated carbon, that we are talking about. The relevant media or the phase which is adsorbing the compounds of interest. What is adsorbate? The chemical or the compound which is being adsorbed onto the media is the relevant adsorbate, adsorbent and adsorbate. So, here this is the adsorbent, the media, and here it is the adsorbate. Right. So, that should clarify it up. Let us move on. So, how do we measure this or express this concentration, and what are the relevant terms and units that I need to look at? So, here we have a new phase, right. It is the solid phase or the adsorbent phase, on which some of your compounds are being adsorbed. So, when you look at the removal, again it is going to be an equilibrium between the compound in the adsorbed phase and the compound in the aqueous phase, right. So, it is a relationship equilibrium typically, yes, and then you are going to also have to express the concentration of the relevant compound on this media. So, we have to look at these variables, let us just look at them. So, what do we have here? This is the media, my adsorbent, and it is suspended in my solution. Here it is not a bed, it is suspended. The concentration is C solid, let us say. We will look at these relevant aspects later. So, C solid, okay, it is grams of the solid per liter of solution, right, grams of solid per liter of solution. And what is it trying to remove? It is trying to remove my particular what do we say, compound of interest. So, here I guess we are using the general aspect, but the granular activated carbon is not used for removing metals, but we are looking at the general figure to be able to understand the different terms and the kinds of units, right. So, dissolved adsorbate, right, the compound which is dissolved, the adsorbate which I want to remove, and it is present at CCU, I guess, right. Okay. So, this is something we are already what do we say, familiar with. And adsorbed species with adsorption density of Q milligrams of copper per grams of solid or per meter square. So, here this copper is adsorbed onto the media, right. The copper is adsorbed onto the media, and I want to know how much copper is adsorbed per mass of media. So, that is what it gives Q, right. Where is this? Milligram adsorbed per gram of adsorbent. This is typically used widely, this particular nomenclature. And then what else do we have? Adsorbed species present at an overall concentration. If I want to know the overall concentration that is adsorbed, then I guess it is going to be milligrams adsorbed per liter. How will I get that? Here it has to be milligrams adsorbed, that I will get from Q in the numerator in Q, and then I want liter in the relevant denominator, right. So, I have to multiply Q with the concentration of the solid in the solution, then I will get mass adsorbed per liter of solution. But again, this is not widely used. Q is the factor or variable that is widely used. And another aspect is surface area per gram of solid is the specific surface area, but we will probably not go into that detail here, right. So, aspect to note is Q, mass of the adsorbate per mass of the adsorbent, right. Mass adsorbed of the adsorbate per mass of the adsorbent, milligram per gram, right, typically. So, types of pollutants to be removed: synthetic organics, as in now we are, due to different lifestyles, we are using different kinds of compounds, let us say personal care products and such, and these are synthetic organics which I do not want to be present in the water that I am supplying to my population. So, some of them can be removed. Color forming organics, even in the dyeing wastewater industry, some people try to use activated carbon to remove some types of compounds which can cause color. Taste and odor causing chemicals, and some disinfection byproduct precursors, typically organic matter or natural organic matter, let us say, right. Again, typically organic compounds and those which are relatively hydrophobic, which do not want to stay in the water, that is the key aspect here. So, adsorption phenomenon. So, what is going to happen, right, or how is it going to happen? During the process, the compounds which are dissolved in the aqueous phase, meaning in water, are transported into the porous solid. So, the GIC that we are going to look at is porous, right. We will have a pretty good figure, but let me draw a very rough figure here. So, this is the pore here. So, the compound which is traveling out here along with the water, it is going to be, what do we say, it is going to be transported to this porous solid. And what is it, what is the phenomena? It is by diffusion, let us say, right. And then it is going to be adsorbed onto the inner surface of the adsorbent. So, that is the relevant aspect. Dissolved species are concentrated on the solid surface by two relevant mechanisms. One is chemical reaction, which is chemisorption, which is pretty rare in adsorption for water treatment, and the other one is physical process based or physical attraction based or physical adsorption. This is the one that is widely relevant to us in the context of water treatment, let us say. This is irreversible typically, and this is typically reversible. Irreversible, typically this is reversible, let us say, right. So, that is something to keep in mind. So, this is a great figure. This is the figure of the granular activated carbon. The carbon matrix is presented here. So, we have large pores and then we have small pores. That is something to keep in mind, right. So, this granular activated carbon, a typical media used for adsorption, has different kinds of pores, as in it is not homogeneous. That is one thing to keep in mind, it is heterogeneous. So, that is one aspect. So, you have large and small organic molecules. So, pores available to both small and large molecule adsorption, that is one thing. And then due to size, some of the bigger molecules will not be able to go through to the other surfaces that are available, but they will be available to the small molecules, right. So, that is something to keep in mind. Yes. So, causes, why is it that this compound wants to be adsorbed onto this media, which is the granular activated carbon? The GAC is the example that we are using. There are different adsorbents obviously, but the one that is most widely used, at least for tertiary treatment or after tertiary treatment or in tertiary treatment, is GAC, let us say. So, the driving force is hydrophobicity, dislike of the water phase, right? And then attraction to the sorbent phase. It wants to leave the water, and then why does it want to be adsorbed onto the surface? Van der Waals forces, physical attraction, let us see, right? And this is the most what do we say widely relevant one, especially for removal of or the applications in water. And this van der Waals forces, why is that coming into play? It is based on the structure of the GAC, right? And that is where it comes into play. Electrostatic forces, surface charge interaction, chemical forces, yes, but here in general we are not concerned with chemical forces, at least in the or chemisorption in the context of what we are discussing here. Primarily it is the physical forces or physical attraction or physical sorption, let us see, or physical adsorption. So, physical adsorption, the forces of attraction include only physical forces and exclude covalent bonding with the surface and also the Coulombic attraction of unlike charges. Again, we are looking at only the physical forces excluding covalent bonding with the surface. And physical adsorption is less specific with respect to the compounds, with respect to which compounds adsorb onto the surface sides. It is not picky, right. So, that is one thing, and it is relatively weaker, right, and energies of bonding, has weaker forces and energies of bonding, operates over long distances. Why is that relevant? As can be seen here, there are multiple layers, let us say. So, you with respect to GAC, you can have one layer of adsorption, then a second layer, third layer and such. So, it will allow for multiple layers and is relatively more reversible. Why is this important? For example, I am using GAC to treat or remove some of the organics from my water. Obviously, here the media, let us say, has a certain capacity. Think of me as being the media, and a poor analogy is that I am trying to take up some of the organic content on my skin. After certain time, most of the skin or my surface will have or will be filled up with the organic content. So, my skin or my surface is not available or does not have any more adsorption sites. So, then I have to do what now? I can dump the activated carbon in a hazardous waste treatment, storage and disposal facility at high cost, and also that space is limited, or you can regenerate it, as in you can what do we say, reverse this physical adsorption. But please note that along with physical adsorption, some of the adsorption is going to be chemisorption or chemical adsorption, that is irreversible. So, even after regeneration, your particular media won't have or the adsorption capacity similar to the virgin granular activated carbon. It is going to lose some of its adsorption capacity, let us see. Different aspects, one is that chemisorption, let us see, right. So, that is the aspect relevant to more reversibility. So, chemical adsorption occurs when the adsorbate reacts with the surface to form a covalent or an ionic bond, right. And they generally cannot accumulate at more than one molecular layer because of the specific bond between adsorbate and surface. So, this chemical adsorption, it is specific, right. So, it can't form multiple layers. So, it is specific to that particular site at that particular location, let us say, due to the characteristics of both that adsorbent and the adsorbate. So, it is specific. So, it can't form beyond one particular layer, let us see. That is something to keep in mind. The bond may also be specific to particular sites or, as I mentioned, functional groups on the surface of the adsorbent. This is what we just discussed. And another aspect which we discussed in another context, coagulants, we know that can form precipitates, FeOH thrice the solid, ferric or aluminum hydroxides. These can have OH surface groups, right. This is the OH surface group and this is the precipitate out here. This is the OH surface groups, and these can adsorb humics and metals. And this is what we discussed when we talked about removal of NOM in the context of what do we say, coagulation, flocculation and then precipitation. We saw that some of the NOM can be removed. How is that? So, this is the relevant principle, adsorption was occurring there. So, this is my particular organic compound, humic substance, where R is representative of the organic compound, let us say COO minus. Again, this depends on the pH 2 obviously. So, what happens? OH minus is released and this COOH, I guess COO minus, that is going to be bound to this particular precipitate or the metal oxide surface and it is going to be removed, let us see. That is something to keep in mind. So, comparison of adsorption mechanisms. Physical adsorption is the predominant one that is used for or that comes into play with respect to water treatment, relatively rare in water treatment though. Process speed, what is the limiting factor? It is limited by mass transfer, as in the water or the compound is flowing here and this is my media, let us say, right, this is my media, right, and so this has to be transported to the media surface, right, it is limited by mass transfer. Type of bonding, it is non-specific, but in general we are dealing with van der Waals forces of attraction. Here it is specific exchange of electrons or chemical bond at the surface, let us see, and thus this particular physical adsorption is reversible while the chemisorption is typically non-reversible, and both are exothermic, but if you look at the heat of adsorption, it is 4 to 40, relatively less for physical and much higher for chemisorption. Again, that is one of the reasons with respect to the weaker and stronger bonds, that is something to keep in mind, but for our context here we are primarily concerned with physical adsorbent. So, how do I choose or what do I need to look at when considering choosing adsorbents, let us see. So, as I mentioned, typically we use granular activated carbon and sometimes powdered activated carbon, but this is not as much used in practice. Key aspect difference is that granular and powdered, the size of the relevant particle is the relevant issue or concern or the distinguishing factor between GAC, granular activated carbon, and powdered activated carbon, let us see, right. So, how is it that you are going to manufacture this particular GAC or PAC? So, first raw materials, different types of woods or such, coir. So, sizing, key aspect is that as you can see everything comes to carbonization, that is one aspect, and after carbonization we have what is called activation. So, two aspects, carbonization and the other one is activation, and then sieving to look at the size or separating the size, the bigger ones GAC, smaller ones PAC. If you want PAC, obviously you can grind it and then get PAC. So, now let us look at what this carbonization and activation is and what the raw materials are, right. So, raw materials, wood, coal, coconut shell, etc. let us see. Again, the key aspect is carbonaceous material, and again here I have organic content, it is organic matter in a way. So, what am I trying to do? I am going to try to liberate the carbon. How am I going to do it? I am going to heat it in the absence of oxygen. It is not oxidation of the carbon, right, and it is just liberating carbon or carbonation, let us say. So, it is heated in oxygen starved environment, which is pyrolysis, let us see, right. So, this is what we have, pyrolysis, and we are liberating the carbon here. This carbonized material is then exposed to steam or hot carbon dioxide. Why? Because I want to form these pores and fissures, right, which will lead to increase in the surface area, let us see, and this is activation. One is carbonization or carbonation and the other one is activation, one to liberate the carbon and the other one to activate the relevant surface area. So, it is granular activated carbon, let us see, right. So, that is something to keep in mind. Creates carbon to which chemical will sorb or adsorb, right. Increases surface area for sorption. One is creating this carbon onto which the chemical will adsorb, the other one is creating the surface area, right. One aspect to note is that let us say per 1 gram of this activated carbon you will have maybe what 1000 meter square of surface area or such, 1000 meter square 100 by 100 I guess, no, not 100 by 100, 100 into 10, right. So, not as big as a soccer field, but you can understand the surface area that will be captured in 1 gram of this activated carbon, but let us look at the data before I go forth. So, depending upon the type of source, you will have different oxygen containing surface groups on the activated carbon, right, which play a role in this particular adsorption, let us see, right. So, that is something to keep in mind, and this is what it looks like when we look at it close up, let us see. And how are we doing that? We are doing with scanning electron microscopy or micrographs, let us see. Scanning electron micrographs for lignite based, it is based on lignite based activated carbon. So, here we have 100 micron, 30 micron scale, 10 micron and 1 micron, let us see. So, this is the scale, this is 100 micron, this is 30 micron, this is 10. So, progressively, you know, progressive magnification, let us see. So, here you can look at the heterogeneity with respect to the pore sizes, right, and you can see how many pores are there in this particular 100 micron what do we say magnified surface, let us see. You can see the number of surfaces available or number of sites available for adsorption, and this is pretty clear when I magnify it further, the bigger, smaller pores, let us say, right. So, all this inside also you will have the surface available for adsorption. This is something that we looked at earlier. So, much more magnified, you see this, and again you have other smaller what do we say groups or pores out here, again further magnification. You see that it is remarkably heterogeneous and it is not homogeneous, that is something to keep in mind. So, this is what we looked at earlier, right, or this is the figure. So, we saw the bigger pores, we saw the smaller pores and so on and so forth. So, depending upon the pore size and the time available, you are going to have the compounds of interest being adsorbed all over this activated carbon. So, over time obviously the relevant surface area is going to be completely taken up by this particular adsorbent, right, or adsorbate, pardon me, adsorbate, which is going to be accumulating on the surface of this adsorbent, which is the GAC. And then what do you need to do? You will need to typically dispose it and put in fresh one. In general, in water or at least with respect to water treatment, they do not use regenerated activated carbon, right. So, that is one thing to keep in mind. Let us look at the characteristics of some GAC. So, raw material, different types of raw material and the kind of coded or code for the activated carbon. So, bed density is different and particle density is different, let us see, right. Bed density, again packing I guess will play a role. So, particle density, again different particles have different densities. Radius also differs slightly, and surface area, as you can see, 875 meters square per gram. So, my earlier estimate of 1000 meters square per gram was not way off, right. So, per just 1 gram of activated carbon, you are having almost 1000 meters square of the relevant area. And one other aspect to keep in mind is that the pore volume is taken up by pores of different sizes, micro, meso and macro, right. Again, you would want a fine balance between these what do we say kinds of pore sizes. Why? Well, if you have everything to be small pores, that is not going to be beneficial, because your compounds of interest might be relatively what do we say across a diverse range with respect to size. And also if you have too fine pores, they can be what do we say, I should not use the term choke, but that is the layman's term, let us say, right. So, you want to have heterogeneity or greater diversity here, right. So, that is what you have out here, and this is the activated carbon tank, typical activated carbon tank. So, there are different ways, bottom up or top bottom, right. So, here you have top to the bottom influent and then some head and it coming out of here, or sometimes it is going to be pressured and pumped up, right. And you can know there are different ways to look at or understanding when this activated carbon has been exhausted, as in this is my media here, right. This is my media. As the water is passing through that, the compounds or the adsorbate in the relevant solution is being adsorbed onto the adsorbent, which is the granular activated carbon, right. So, after time this will be exhausted. So, there can be indications if you are actually paying attention to the plant and the plant manager or operator is taking samples at regular intervals. You see the different sampling ports, right. For example, here this water is coming in contact here. So, most of this will first be exhausted, and then this exhausted layer will come down and then you will have breakthrough. We will look at this. Sampling ports will give you an idea about when this might happen. So, sampling ports will give you an idea about where this particular active or mass transfer zone is, and then you can predict when that is going to be exhausted, right. Or one other way is to look at the amount of pressure or head, that is head loss that is occurring, let us say. That will also give you an idea about when you need to backwash or if it is already exhausted. Typically, we look at head loss for looking at how frequently you need to backwash the relevant surface, not surface, the media. So, that is what you see backwash setup to, right. So, factors affecting adsorption, obviously different kinds of activated carbon and different properties, chemical properties of the adsorbate, aromatic, aliphatic and such, right. Is it hydrophobic, hydrophilic and such, pH of the water, certainly as you can see some cases the pH will decide the charge on the relevant NOM or such, but in general at what do we say, pH neutral range, we are fine with respect to it, as in most of it will be, I guess, negatively charged. But one aspect I want to note here is that we talk about polar compounds and non-polar, right. So, polar compounds which are hydrophilic will not be removed by adsorption typically. Why is that? Let us say they have charge, negative charge, relatively negative charge, and then water, again polar solvent, let us say, right, and they have liking for each other, right, and this compound that has charge on it will not leave or find it difficult to leave the aqueous phase and be adsorbed onto the adsorbent, right. So, that is something to keep in mind, but if the compound is relatively non-polar, right, and then that is going to be adsorbed onto your relevant surface. So, in these cases sometimes the pH will also play a role, that is something to keep in mind. Again temperature of water too, but mostly we are looking at these three aspects though, right. Let us move on. Again, for example, humic acid, huge compound, let us say, humic and fulvic acids, parts of the natural organic matter, let us say, right, and these again can have charge, typically do have charge, but with respect to their solubility, they are relatively less soluble. Why? Because of the structure, aromatic, aliphatic, typically aromatic, they have a lot of these aromatic rings, they are thus not very much soluble in water. Yes. So, one other aspect to look at understanding whether a compound will be easily adsorbed onto the media or not is looking at solubility of the compound of interest. If the compound of interest has low solubility in water, right, that will typically indicate that it will be relatively easily adsorbed or more adsorbed or wants to be adsorbed onto your adsorbent. So, that is something to keep in mind, let us see. So, let us move on. So, we are now going to move on to adsorption isotherms. What is this? So, and why is this relevant? Here we are talking about understanding the relationship between the concentration in the water or the bulk liquid phase, concentration in the aqueous phase, and the concentration of the relevant compound of interest on the adsorbent, right. There is going to be an equilibrium between them. So, assuming that we have a limited number of sites and you have relatively more concentration of your particular compound in the relevant water, at equilibrium obviously the concentration, this Q is also going to be relatively higher, right. It is going to be a equilibrium relationship between the two phases, let us say, right, again allowing for mass transfer to be relatively immediate, let us say, yes, or relatively effective mass transfer. So, here I want these isotherms to be able to predict what will be the equilibrium concentration in the aqueous phase, as in if I use this adsorbent, will I be able to achieve the level of what do we say, desired compound concentration at the effluent that I want, and also how much is the adsorbent that I need to keep for this or use for this volume of liquid, let us say. And these are the questions which will be or can be answered by these adsorption isotherms. So, that we will get it done in the next session. Thank you.